everybody, welcome. So we're going to talk today about what's known as the quantum mechanical model of the atom. And to do this, I first want to, talk about what happened with Niels Bohr. His model, we still use it today in a lot of ways. Biologists use it in biology. We use it in Regents chemistry. But in reality, his model, it was based on a lot of mathematics, and those mathematical formulas just don't work for atoms that are more complex. And so his equations really only worked for hydrogen. He had a single electron model. When he tried to have more than one electron in the atom, things started to get more complicated and they fell apart. And at the same time, scientists were discovering things about matter, the nature of matter, that was sort of, saying to them the model of the atom is a lot more complex than we think. And one of those scientists was DeBroglie. And what DeBroglie saw was that there's this wave nature to matter. And what you can actually do is you can derive his equation, but really the most important part is right down here. And what he said was that you have this wavelength of matter that is equal to Planck's constant divided by the mass times the speed. Now, to go over this, we have h that has the units joules times seconds. The mass to match up with the joules has to be in kilograms, and the speed has to be in meters per second. Now, once de Broglie discovered this, a lot of people started manipulating the wave nature of matter, and we see that all over the place. One way to look at it is with electrons. Electrons actually have a very pronounced wave property, and you can use these wave properties of electrons to focus the beam of electrons, shoot it at a target, and generate an image from it. Because the electron's wavelength is so tiny, the image that you get is much, much smaller and is much more microscopic than you can get with just regular light. This is how the electron microscope works. So you can see these, tiny little beasts that you could never see with your eye, and even if you saw it under a light microscope, they would look like little specks. Now these electrons, they are being manipulated in this device here, the electron microscope. But if we look at electrons that naturally exist in atoms, they also have wavelengths because they're moving with a speed. And the thing about these electron wavelengths is that they can only vibrate with certain frequencies. The result of these vibrations with these certain frequencies creates areas in the atom called orbitals. And this is a probability function. It is where electrons are most likely to be found. So electrons in atoms, they have almost like a standing wave property to them. I'll show you a really great video of standing waves so you can kind of see, what it would look like to see a large standing wave. Now, it's important to note that we use this term orbital here, but it's not the same as a circular orbit that you would find in Bohr's idea. But because the electrons can only be found in certain regions of space called orbitals, they do have a certain energy associated with them. So the idea of energy levels, that's still valid and still really important. We're still going to use the term energy level when we describe electrons and atoms. But now we're going to go deeper and we're going to understand what electrons look like in terms of the orbital space that they occupy. Now, before we go on and talk a little bit about, what an orbital is, let's try a de Broglie practice problem. So let's set up our equation here. Let's look at what an electron's wavelength would be inside an atom. And so let's say that we find the wavelength of the electron to be Planck's constant, 6.63 times 10 to the negative 34th, divided by its mass in kilograms. So that's 9.11 times 10 to the negative 31 kilograms, times its speed in meters per second, 3.25 times 10 to the 5th meters per second. So if we go ahead and we try and solve for this now in my calculator, and I do 6.63 e to the negative 34th, and I divide that by 9.11 e to the negative 31, and then I divide that answer by 3.25 e to the fifth, I get an answer that is 36789, 2.2 times 10 to the negative 9 meters, so this is about 2.2 nanometers. So you can see the wavelength is really small. You can't see electrons moving. But at the same time, though, within an atom, that is a wavelength that could be reasonable. We can practice a few more DeBroglie practice problems in class, but let's talk a little bit more about what an orbital is. Really, what an orbital is, it's a mathematical equation. So an orbital is sometimes called the wave function because it is based on a mathematical formula. This equation, when you square it, just like anything else in probability, it's going to give you an idea of where the electron's located. This is called the orbital, and it's only based on probability. It's about 90% correct. What you end up getting is if you have your nucleus here, and you have your electron around it, which we can do in blue, your electron could be at any point at any place here, and so you get like an archery map, a well-used archery target. Or some of you have that Find My iPhone app, or where it's the location services. If your parents turn that on and install the app on their phone, they can actually map where you are. And so this would be like each dot would be where you were spending time each day. Obviously studying chemistry in your room. But here we have this cloud that forms. Where we have the darker spots, an electron's more likely to be. There's still a boundary to this that's based on the wavelength of the electron. The electron can't be found outside of a certain region because its wavelength would become what's known as destructive interference, and it won't work properly. The electron will never be found in that area. They call that a node. Where an electron can be found, that is where you would find it in an orbital. So what is an orbital? It just corresponds to the specific wave function that can be solved for using the complicated math equations. Now you will not be asked to solve these wave functions. This is something that you would do if you were a chemistry major in college and you were taking a year-long course called quantum mechanics or physical chemistry. You would do a lot of this stuff in there. But for us, we just want to know the concept of what an orbital is. These equations that, you could solve for, I actually show you the difficulty of the math on a few pages down. And this might look like, what are they talking about? But these are the wave functions for different orbitals in an atom. Each wave function is unique to each orbital and where you would find an electron. Let me repeat that I will in no way ask you to solve for these or use these equations, but I get the question a lot of, I say that there's an equation and I don't put it up and people want to know what it is. So here it is. You'll notice that there's terms in the equation that they're using, M and L. And those are the descriptors for the orbital where you would find an electron. What do these correspond to? Well, the first one is N. It is called the principal quantum number. Basically what it tells you is, it tells you the principal energy level, the size of the orbit or orbital. So this is the distance from the nucleus. So the larger that number, the larger the orbitals are within that principal energy level. The second number that describes an orbital is called the secondary quantum number, or the azimuthal number, and it's given the symbol L. And this describes the shape of the region of space where you would find the electron. This is also known as the sublevel. The sublevel has numbers, and they are related to the principal energy level. They can be equal to n minus 1 down to 0. For example, if I have an energy level n equals 4, I can have an L that is equal to 3, 2, 1, or 0. The next number that describes an electron in an orbital is called the magnetic quantum number. It actually tells you the coordinates on a x, y, and z axes of where you would find the orbital. And this is plus or minus L. So if I gave you an L from above here of 3, your ML is equal to -3, -2, -1, 0, 1, 2, 3. What this tells me is how many orbitals there are, how many different regions of space where I could find an electron. And so when I look at this and I say, all right, well, how many different orbitals are there? Well, 1, 2, 3, 4, 5, 6, 7 orbitals. And the last number is called the magnetic spin. The magnetic spin is telling me about the electron spin. And it can either be an up arrow for an electron spinning in a half, or -1/2 for an electron spinning down. Those are my two possibilities for my magnetic spin. Now I know that this is complicated and sort of like, what is he really talking about here? Because it's out of context in a sense. And so what I'd like to do is kind of put it all together for you. And I'm going to do that on the next slide. Let's say that we have an energy level n equals 1. Well, within that first energy level where you can find an electron, we need to see what the sublevels are. Remember, the sublevels L are equal to n minus 1 all the way down to 0. So I do the subtraction. N minus 1. 1 minus 1 is 0. That actually gets a letter designation S. So when the first energy level 1, there is a sublevel called S, which has a numerical value of 0. Within the S sublevel, this is going to tell me the orbital. The orbital, there's only one orbital. And within each orbital, I can fit 2 electrons. And each electron can be +1/2 or -1/2. I can show this by drawing a box for the orbital. And within the orbital, I can put my 2 electrons, 1/2 and -1/2. My first energy level, 1, is my smallest energy level. It can only hold 2 electrons. After I try and put 2 electrons in, the repulsion becomes so great that they are forced into the second level. In the second energy level, which is bigger, I can figure out my sublevels. So I do my subtraction. For L, 2 minus 1 is 1, and 1 minus 1 is 0. Notice the second energy level has 2 sublevels. Well, how many orbitals do they each have? Well, let's see. S plus or minus L, which is plus or minus 0, so that just has the 1 orbital. P has plus or minus 1, so it has -1, 0, and 1. Each orbital can hold 2 electrons. 1, 2, 1, 2, 1, 2, 1, 2. The second level can hold a total of 8 electrons. The first can hold 2 electrons. Let's try it with the third energy level, n equals 3. N equals 3. The sublevels could be n minus 1, so 2, 1, and 0. 0 will always get the letter designation S, 1 will always get P, 2 will always get D. Let's figure out the orbitals for each one. Plus or minus 0 is 0, so this would have 1 orbital. P, negative 1, 0, and 1 would have 3 orbitals. D, plus or minus 2, negative 2, negative 1, 0, 1, and 2, that is 5 orbitals. The number of electrons, 2, 6, and 10 for D. I want you to try the same thing for 4. I started it for you. S, P, D, and F. The fourth energy level can have a sublevel called 3, 2, 1, and 0. 0 corresponds to S, P is 1, D is 2, F is 3. I'd like you to finish this off and do this bottom part here for me, just like I did for the other ones, and tell me how many electrons total you would have in each of them. For the third level, we have 18 electrons total. Tell me what you would have in each of the sublevels and the total for 4. Tomorrow in class, we'll go through all this. Again, here are the equations, and here are the values. They go up to the third level. But, you can see the different energy levels here. We can do that in this red color. Okay, so those are the energy levels there. Then they do the sublevels. So here are the sublevels. Sublevel, 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 sublevels. And then you also have the orbitals, which you can do in a different color. So for each one, there's the orbitals. Orbitals highlighted here. So why do we care about this? Well, we want to know mathematically what the electrons, or where the electrons are. Again, this is telling us the location of an electron based on its coordinates, its distance from the nucleus, the shape of the region of space where it is, its XYZ coordinates, and the spin of the electrons. Will you be asked to do this on a test? Well, you'll be asked to find what are acceptable quantum numbers, or the quantum numbers of a last electron in an atom. That you'll be asked to do. The main thing that I really want you to be able to do is electron configurations. But that we're going to save till next time. Alright, so tomorrow we'll review all the history of the atom, we'll talk about Bohr, and then we'll go on to talk more about these quantum numbers, and maybe even get a chance to start some of the electron configurations. Alright, thanks so much.